Alright, hello everyone, and welcome to my channel. This is an educational channel. We look at theories of everything, ancient and modern, do deep dives on them, and try to illustrate how they can be used in your own life to help you with your paradigm shifting, your awakening to 5D consciousness, and your formation of a holistic worldview. Today is our 510th video that we've done on Dewey B. Larson and his reciprocal system of theory. And Mr. Larson lived in the 20th century. He was a chemical engineer, I believe, and he lived out in Portland most of his life, born in North Dakota. And around 1930, he had some epiphanies about the nature of the universe. Long process of inductive reasoning eventually led him to put out his two fundamental postulates in 1959. And from there, a process of deductive reasoning led him to articulate his theoretical universe, what his universe would look like if his postulates were correct. And then he wrote books where he compared his theoretical universe with the actual so-called measured and compiled universe of modern science, the scientific tables. So, for example, we are looking at today his book called Basic Properties of Matter, which is on chemistry. Larson arrives at equations for many of the basic properties of matter, like the melting point, and then he plugs in his formulas to all of the atoms and many compounds, and then compares them with the scientific tables that are already out there. And it's telling that he's able to at least partially recreate the scientific tables strictly from theory. We are about to start chapter 21 of that book called Electromagnetism. Now, if you'd like a little deeper dive into the reciprocal system, understand some of the basic aspects of it, you want to watch one of my first 474 videos on this subject, where I go at least 20 minutes on the basics of the reciprocal system. I'm just going to more or less assume that you have a grasp of the basics of the reciprocal system for the purpose of this video. I'm just going to move forward here with the stuff on electromagnetism. Okay, chapter 21. Now, you might be able to follow along anyway, because Larson might be explaining some of his basic concepts here, but I can't guarantee that. So you may be in the dark, but it may, if you are inclined toward mystery, you might be able to figure out some of it. Okay, chapter 21, electromagnetism. The terms electric and magnetic were introduced in volume 1 with the understanding that they were to be used as synonyms for scalar one-dimensional and scalar two-dimensional, respectively, rather than being restricted to the relatively narrow significance that they have in common usage. These words have been used in the same sense in this volume, although the broad scope of their definitions is not as evident as in volume 1, because we are now dealing mainly with phenomena that are commonly called electric or magnetic. We have identified a one-dimensional movement of uncharged electrons as electric current, a one-dimensional rotational vibration as an electric charge, and a two-dimensional rotational vibration as a magnetic charge. More specifically, The magnetic charge is a two-dimensional rotationally distributed scalar motion of a vibrational character. Now we are ready to examine some motions that are not charges, but have some of the primary characteristics of the magnetic charge. That is, they are two-dimensional, directionally distributed scalar motions. Let us consider a short section of a conductor through which we will pass an electric current. The matter of which the conductor is composed is subject to gravitation, which is a three-dimensional distributed inward scalar motion. As we have seen, the current is a movement of space, or electrons, through the matter of the conductor, which is primarily made out of time, equivalent to an outward scalar motion of the matter through space, or really mutual through outward scalar motion of the matter through space is the inward, the motion of electrons through matter. Thus, the one-dimensional motion of the current opposes the portion of the inward scalar motion of gravitation that is effective in the scalar dimension of the spatial reference system. For purposes of this example, let us assume that the two opposing motions in this section of the conductor are equal in magnitude. The net motion in this scalar dimension is then zero. What remains of the original three-dimensional gravitational motion is a rotationally distributed scalar motion in the other two scalar dimensions. Since this remaining motion is scalar and two-dimensional, it is magnetic and is known as electromagnetism. In the usual case, the gravitational motion in the dimension of the current is only partially neutralized by the current flow, but this does not change the nature of the result. It merely reduces the magnitude of the magnetic effect. From the foregoing explanation, it can be seen that electromagnetism is the residue of the gravitational motion that remains after all or part of the motion in one of the three gravitational dimensions has been neutralized by the oppositely directed motion of the electric current. Thus, it is a two-dimensional scalar motion perpendicular to the flow of current. Since it is the gravitational motion in the two dimensions that are not subject to the outward motion of the electric current, it has the inward scalar direction. In all cases, the magnetic effect appears much greater than the gravitational effect that is eliminated when viewed in the context of our gravitationally bound reference system. This does not mean that something has been created by the current. What has happened is that certain motions have been transformed into other types of motion that are more concentrated in the reference system, and energy has been brought in from the outside to meet the requirements of the new situation. As pointed out in Chapter 14, this difference that we observe between the magnitudes of motions with different numbers of effective dimensions is an artificial product of our position in the gravitationally bound system, a position that greatly exaggerates the size of the spatial unit. From the standpoint of the natural reference system, the system to which the universe actually conforms, the basic units are independent of dimensions. That is, 1 to the third equals 1 squared equals 1. But because of our asymmetric position in the universe, the natural unit of speed, s over t, takes the large value of 3 times 10 to the 10th centimeters per second. And this becomes a dimensional factor that enters into every relation between quantities of different dimensions. For example, the c² term, the second power of 3 times 10 to the 10th, in Einstein's equation for the relation between mass and energy, reflects the factor applicable to the two scalar dimensions that separate mass, t to the third over s to the third, from energy, t over s. Similarly, the difference of one dimension between the two-dimensional magnetic effect and the three-dimensional gravitational effect makes the magnetic effect 3 times 10 to the 10th times as great when expressed in CGS units. The magnetic effect is less than the one-dimensional electric effect by the same factor. It follows that the magnetic unit of charge, or EMU, defined by the magnetic equivalent of the Coulomb law, is 3 times 10 to the 10th times as large as the electric unit, or ESU. The electric unit is 4.80 times 10 to the minus 10th ESU, is equivalent to 1.80 times 10 to the minus 20th EMU. The relative scalar directions of the forces between current elements are opposite to the directions of forces produced by electric and magnetic charges, as shown in Figure 23, which should be compared with Figure 22 of Chapter 19. The inward electromagnetic motions are directed toward the 0 points from which the motions of the charges are directed outward. Two conductors carrying current in the same direction, AB or A'B, analogous to like charges, move toward each other, as shown at the top line of the diagram, instead of repelling each other as like charges do. Two conductors carrying current in the direction BA or B'A, as shown in the third line, also move toward each other. But conductors carrying current in opposite directions, AB' and BA', analogous to unlike charges, move away from each other, as indicated in the middle line. These differences in origin and in scalar direction between the two kinds of magnetism also manifest themselves in some other ways. In our examination of these matters, we will find it convenient to consider the force relations from a different point of view. Thus far, our discussion of the rotationally distributed scalar motions, gravitational, electric, and magnetic, has been carried out in terms of the forces exerted by discrete objects, essentially point sources of the effects under consideration. Now, in electromagnetism, we are dealing with continuous sources. These are actually continuous arrays of discrete sources, as all physical phenomena exist only in the form of discrete units. It would therefore be possible to treat electromagnetic effects in the same manner as the effects due to the more readily identifiable point sources. But this approach to the continuous sources is complicated and difficult. A very substantial simplification is accomplished by introduction of the concept of the field discussed in Chapter 12. This field approach is also applicable to the simpler gravitational and electrical phenomena. Indeed, it is the currently fashionable way of handling all of these apparent interactions, even though the alternate approach is, in some ways, better adapted to the discrete sources. In examining the basic nature of fields, we may therefore look at the gravitational situation, which is, in most respects, the simplest of these phenomena. As we saw in Chapter 12, a mass A has a motion AB toward any other mass B in its vicinity. This motion is inherently indistinguishable from a motion BA of atom B. To the extent that actual motion of mass A is prevented by its inertia or otherwise, the motion of object A therefore appears in the reference system as a motion of object B, constituting an addition to the actual motion of that object. The magnitude of this gravitational motion of mass A that is attributed to mass B is determined by the product of the masses A and B, and by the separation between the two, as is the motion of mass B. If the scalar motion AB is regarded as a motion of both objects, it then follows that each spatial location in the vicinity of object A can be assigned a magnitude and a direction, indicating the manner in which a mass of unit size would move under the influence of the gravitational force of object A if it occupied that location. The assemblage of these locations and the corresponding force vectors constitute the gravitational field of object A. Similarly, the distribution of the motion of an electric or magnetic charge defines an electric or magnetic field in the space surrounding this charge. The mathematical expression of this explanation of the field of a mass or charge is identical with that which appears in currently accepted physical theory, but its conceptual basis is entirely different. The conventional view is that the field is something physically real in the space around the originating object, and that the force is physically transmitted from one object to the other by this something. However, as P.W. Bridgman concluded after carrying out a critical analysis of this situation, there is no evidence at all to justify the assumption that this something actually exists. Our finding is that the field is not something physical. It is merely a mathematical consequence of the inability of the conventional reference system to represent scalar motion in its true character. But this recognition of its true status as a mathematical expedient does not negate its usefulness. The field approach remains the simplest and most convenient way of dealing mathematically with magnetism. The field of a magnetic charge is defined in terms of the force experienced by a test magnet. The field of a magnetic pole, one end of a long bar magnet, for example, is therefore radial. As can be seen from the description of the origin of electromagnetism in the foregoing paragraphs, the field of a wire carrying an electric current would also be radial in 2 dimensions if it were defined in terms of the force experienced by an element of the current in a parallel conductor. But it is customary to define the electromagnetic field on the magnetostatic basis, that is, by the force experienced by a magnet or an electromagnet in the form of a coil or solenoid, which produces a radial field similar to that of a bar magnet by means of its geometrical arrangement. When the field of a current-carrying wire is thus defined, it circles the wire rather than extending out radially. The force exerted on the test magnet is, then, perpendicular to the field, as well as to the direction of the current flow. Here is a direct challenge to physical theory, an apparent violation of physical principles that apply elsewhere. It is a challenge that has never before been met. The physicists have not even been able to devise a plausible hypothesis, so they simply note the anomaly, the strange characteristics of the magnetic effect. Quote, "The magnetic force has a strange directional character," says Richard Feynman. At every instant, the force is always at right angles to the velocity vector. End quote. It is likely, however, that this perpendicular relation between the direction of current movement and the direction of the force would not seem so strange if magnets interacted only with magnets and currents with currents. In that event, the magnetic effect of current on current would still be at right angles to the velocity vector, but it would be in the direction of the field rather than perpendicular to it, as the field would have to be defined in terms of the action of current on current. When there is interaction between current and magnet, the resultant force is perpendicular to the magnetic field, that is, to the field intensity vector. A test magnet in an electromagnetic field does not move in the direction of the field as would be expected, but moves in a perpendicular direction. Notice how strange the direction of this force is. It is not in line with the field, nor is it in the direction of the current. Instead, the force is perpendicular to both the current and the field lines. The use of the word strange in the statement is a tacit admission that the reason for the perpendicular direction is not understood in the context of present-day physical theory. Here again, the development of the theory of the universe of motion provides the missing information. The key to an understanding of the situation is a recognition of the difference between the scalar direction of the motion of the magnetic charge, which is outward, and that of the electromagnetic motion, which is inward. The motion of the electric current obviously has to take place in one of the scalar dimensions other than that represented in the spatial reference system, as the direction of current flow does not normally coincide with the direction of motion of the conductor. The magnetic residue therefore consists of motion in the other unobservable dimension and in the dimension of the reference system. When the magnetic effect of one current interacts with that of another, the dimension of the motion of current, A, that is parallel with the dimension of the reference system, coincides with the corresponding dimension of current, B. As indicated in Chapter 13, the result is a single force, a mutual force of attraction or repulsion that decreases or increases the distance between B and A. But if the interaction is between current A and magnet C, the dimensions parallel to the reference system cannot coincide, as the motion and the corresponding force of the current A is in the inward scalar direction, while that of the magnet C is outward. It may be asked why these inward and outward motions cannot be combined on a positive and negative basis with a net resultant equal to the difference. The reason is that the inward motion of the conductor A toward the magnet C is also a motion of C toward A, since scalar motion is a mutual process. The outward motion of the magnet is likewise both a motion of C away from A and a motion of A away from C. It follows that these are two separate motions of both objects, one inward and one outward, not a combination of an inward motion of one object and an outward motion of the other. It then follows that the two motions must take place in different scalar dimensions. The force exerted on a current element in a magnetic field, the force aspect of the motion in the dimension of the reference system, is therefore perpendicular to the field. These relations are illustrated in Figure 24. At the left of the diagram is one end of a bar magnet. This magnet generates a magnetostatic field. which exists in two scalar dimensions. One dimension of any scalar motion can be so oriented that it is coincident with the dimensions of the reference system. We will call this observable dimension of the MS magnetostatic motion A, using the capital letter to show capital A, using the capital letter to show its observable status, and representing the magnetostatic field by a heavy line. The unobservable dimension of motion is designated B and is represented by a light line. We now introduce an electric current in a third scalar dimension. As indicated above, this is also oriented coincident with the dimension of the reference system and is designated as C. The current generates an electromagnetic EM field in the dimensions A and B perpendicular to C. Since the magnetostatic motion has the outward scalar direction, while the EM motion is directed inward, the scalar dimensions of these motions coincident with the dimension of the reference system cannot be the same. The dimensions of the EM motion are therefore B and lowercase a. That is, the observable result of the interaction between the two types of magnetic motion is in the dimension B, perpendicular to both the magnetostatic field A and the current C. The comment about the strange direction of the magnetic force quoted above is followed by this statement, quote, "Another strange feature of this force is that if the field lines and the wire are parallel, then the force on the wire is zero." In this case, too, the answer to the problem is provided by a consideration of the distribution of the motions among the three scalar dimensions. When the dimension of the current is C, perpendicular to the dimension A of the motion represented by the MS field, the EM field is in scalar dimensions A, lowercase a, and capital B. We saw earlier that the observable dimensions of the inward EM motion and the outward MS motion cannot be coincident. Thus, the EM motion in dimension lowercase a is unobservable. It follows that the motion in scalar dimension capital B, the dimension at right angles to both the current and the field, has to be the one in which the observable magnetic effect takes place. However, if the direction of the current is parallel to that of the magnetic field, the scalar dimensions of these motions, both outward, are coincident, and only one of the three scalar dimensions is required for both motions. This leaves two unobservable scalar dimensions available for the EM motion and eliminates the observable interaction between the EM and MS fields. As the foregoing discussion brings out, there are major differences between magnetostatics and electromagnetism. Present-day investigators know that these differences exist, but they are unwilling to recognize their true significance because current scientific opinion is committed to a belief in the validity of Ampere's 19th century hypothesis that all magnetism is electromagnetism. According to this hypothesis, there are small circulating electric currents, Amperian currents, in magnetic materials whose existence is assumed in order to account for the magnetic effects. This is an example of a situation very common in present-day science in which the scientific community continues to accept and build upon hypotheses which have been revised so drastically to accommodate new information that the essence of the original hypothesis has been totally negated. It should be realized that there is no empirical support for Ampere's hypothesis. The existence of the Amperian currents is simply assumed. But today, no one seems to have a very clear idea as to just what is being assumed. Ampere's hypothetical currents were miniature reproductions of the currents with which he was familiar. However, when it was found that individual atoms and particles exhibit magnetic effects, the original hypothesis had to be modified, and the Amperian currents are now regarded as existing within these individual units. At one time, it appeared that the assumed orbital motion of the hypothetical electrons in the atoms would meet the requirements, but it is now conceded that something more is necessary. The current tendency is to assume that the electrons and other subatomic particles have some kind of a spin that produces the same effects as translational motion. The following comment from a 1981 textbook shows how vague the Amperian current hypothesis has become. Quote, "At this present time, we do not know what goes on inside these basic particles, electrons, etc., but we expect their magnetic effects will be found to be the result of charge motion, spinning of the particle or motion of the charges within it." Okay, I think we're going to stop. I can read one more paragraph. Ampere's hypothesis was originally attractive because it explained one phenomena, magnetostatics, in terms of the other, electromagnetism, thereby apparently accomplishing an important simplification of magnetic theory. But it is abundantly clear by this time that there are major differences between the two magnetic phenomena, and just as soon as that fact became evident, the case in favor of Ampere's hypothesis crumbled. There is no longer any justification for equating the two types of magnetism. The continued adherence to this hypothesis and use of Amperian currents in magnetic theory is an illustration of the fact that there is inertia in the realm of ideas as well as in the physical world. Okay, we're going to stop there, and we will finish this chapter. Well, I don't know that we'll finish the chapter, but we will continue the chapter tomorrow and hopefully finish it. And please tune in tomorrow. Thanks for tuning in today, and have